And thank you, everyone, for inviting me here today. My name's John Vincent, formerly of industry, the UK Civil Aviation Authority, and EASA here in Cologne. The title of my presentation today is 1 in a billion, and I chose that title because of the almost mythical status of the 10 to the minus 9 figure that we use in system safety assessment. So I'll apologize to any of the more literate members of the audience here. This is more of a basic tutorial, sort of giving people the background as to why we came to that particular safety objective and the nature of safety objectives. So a little bit about IFA first. The International Federation of Airworthiness has been around since the 1970s. It's a charitable organization. We have a seat at the Airworthiness panel in ICAO, entirely run by volunteers. We would welcome new members. We have some industry members, mostly from the airlines and the maintenance communities, but we'd certainly welcome some new members to support our work. So the presentation today, 3 parts. We'll revisit the probabilistic approach. Why is it that we have developed our airworthiness requirements, rules, standards, specifications in this particular way? And I'll talk some of the failures and successes of the use of safety objectives, and at the end talk more about how we are developing towards a performance-based approach and make a proposal at the end of the presentation, a particular proposal related to rule changes which are on the table at the moment. So this is the journey that we're on. We can say the past there is some of the early days of transport aviation, post-war. A lot of the technical requirements, rules, regulations were prescriptive and empirical. A lot of safety work was done by inspection. You, had a look at it. It was safe. Regulators prescribed. This is how you should do things. This is what makes something safe. But progressively over the years, this approach was found to be inadequate to face the technical challenges that were presented. And progressively and slowly, we're migrating towards a more objective and performance-based approach. And 1309, in its many forms across the FARs and the certification specifications, has been the center of that change in terms of introducing a safety objective into the design requirements. Where did it all start? Well, this is CAR 4B, which is going back to the 1950s. Although some of CAR 4B is still applicable to the 737, given the fact that it's a derivative aircraft. And there you have people starting to use probabilistic language. There's a mention of render inoperative by probable malfunction. And the minute you start to use the word probable, the question arises, well, what do you mean by that? How do you measure that? How do you show that that requirement is met? So at that time, it was, as I say, more of a question of inspection. Generation moves on, and we're faced with ever more complex systems, which is kind of pertinent given the presentation we've just received from Thales. The first blind landing systems were introduced in the early 1960s, and they were not simple, they were not straightforward, they were not obviously safe. You would require a level of analysis. The main reason for that is the interdependencies that were introduced by having an airborne system with a critical function and that relationship with the ground-based system. So you have some complex interactions, and you have to discover and understand those complex interdependencies to be able to demonstrate a level of safety that is acceptable to the traveling public. And then the question arises, well, what should that level of safety be? And I can see the VTOL folk are struggling with that at the moment. What should that level of safety be to be acceptable to the public? So the overall high-level objective is that by introducing a new system, it should be no less safe than what it replaces. Ideally, it should offer a safety improvement. But it cannot be certifiable if it is less safe than what it proposes to replace. So you have that high-level objective. At the time, the 60s, sort of mid-60s, the fatal accident rate was about 1 per million landings. Of that, the systems causes were considered to be about 10%. Remember, we're considering all accidents, not just systems causes. So the safety objective was set at 1 per 10 million landings. And that was incorporated in the requirements. The next sort of step change that forced the path of development of that probabilistic approach, the need for a system safety assessment, even further, was Concorde. Because Concorde added another order of complexity to air transport. And in the TSS standards, I still have a copy at home of the safety assessment requirements. You see some of the early language of the 1309 requirement that we apply today. And that's really because of the complexity of some of the systems there, particularly the engine intake, the transition between subsonic and supersonic flight, critical systems. Once you have accepted these principles, we need a generic requirement. So where did the 10 to the minus 9 come from? Now, I've seen several explanations, so please don't take it that this is the only way of explaining the route to the 10 to the minus 9. There are other ways of viewing this, but it's my route to that particular explanation. If we go back to the mid-70s, as requirements were developing, we had about 4 accidents per million flying hours. And of that, all systems, aircraft systems, in a given type, again, we use that 10% figure. And in my days of safety analysis, 10 to 12% systems causes is not unreasonable. It's not easy to put an exact number on it, because there are so many factors involved. But 10 to 12% is about reasonable. So the system safety objective was set at 1 per 10 million hours, all systems on a given aircraft. If we take that a little bit further, in terms of what objectives should we set for an individual failure condition that may cause a catastrophic outcome, then let's assume there are 10 critical systems on a given aircraft. And of those 10 systems, each has 10 potential catastrophic failure conditions. And if you factor that in, that's where you come up with the 1 in a billion. That's where you come up with a 10 to the minus 9 per flight hour as the safety objective for a failure condition creating a catastrophic outcome. And it was embedded in the requirements, and it's been there in 1309 now for many a year, and it's demonstrated actually to be quite successful as a safety objective. Now, dealing with probabilities, you might say 1 in a billion, that's enormous. It's huge. Or tiny, minuscule. But it's not in our everyday lives. Many of you are sitting in front of laptops, with terabyte drives. So big numbers, small numbers, part of our everyday lives now. We take it for granted. It all goes on hidden from us. But these big numbers, these small numbers, are not necessarily alien to everyday life. Now, the aircraft that's almost reached the billion flying hours, if you look at the 737 over its entire history from the 1960s, is the type that gets closest. But if we look at rotorcraft, oil and gas, from the from one of the safety reports recently, we see about 1 million flying hours a year. So the numbers accumulate very rapidly. Underlying are the principles that I've already mentioned, that there should be no increased risk of accident by introducing a new system or a new aircraft type with new systems. But we also, having set one objective, and at the other end of the scale you have, say, no effect. Maybe if I'm carrying my calculator on an airplane, it has no effect on the safety of the aircraft. It might, I suppose, if the battery catches fire. There are other factors to consider. But there are systems of no effect, and there are systems which are critical to the safe flight and continued flight and landing of the aircraft. So you have this inverse proportion. That in itself is not enough. You need to be able to segment that, to explain it. And in the early days of 1309, we divided it into 3. So my certification work in the early 90s, we had 3 levels. Software guidance, we had levels 1, 2, and 3. But it was found again that this was inadequate. The problem being that level 2, that level in the center there, is far too broad. It encompasses far too many systems. And the difference between failure effects at the top end and failure effects at the bottom end are enormous. So as the requirements developed, so that was subdivided. And we have what we have today. 4 basic categories and the proportionality, the inverse proportion relationship embedded in 1309. And I'm glad to see that there's harmonization now occurring. It's not just 25-1309, 23-1309, 27 and 29 are being harmonized around exactly the same set of principles, using exactly the same language, so that we have a common language to talk about a system safety assessment. And it occurred to me with the Thales presentation, where you're taking components from a large transport aircraft, like the smart actuators, and you may be reusing some of that safety data. Then you need that common language, you need that common method, you need a generic expression. In reality, of course, there are 5 levels. I've mentioned no effect. And if many of you are familiar with safety management and using risk matrices, 5x5 matrix is probably the most commonly used. So 1309 has consistency with other safety methods and techniques. So this is what it looks like, where we equate the words with the numbers and demonstrate the proportionality that was inherent in that graph. Now, this is very simplified. I'm not getting into any of the probabilistic mathematics. In fact, it's more to do with the expressions that we use. There's often an argument here in the hazardous category as to whether that means fatalities or not. Certainly for a small type, like a small helicopter, it should not mean fatalities. But if it was a very, very large aircraft, maybe 1 or 2 fatalities that may be considered within that category. So we're harmonizing these definitions, and I think that offers a lot of benefit for the future. Strategies for risk reduction in systems architecture. This is a bit of a teach-in. You guys know this stuff. 1 channel, 2 channels, 3 channels. Nicely, if we look at a very crude analysis here, dealing only with small numbers, say the maths only works with small numbers, 1 in 1,000 failure. Now that's not a good system, really. We should expect better of electronic systems than that. But we can easily meet with a triplex configuration. And that's not always 3 independent similar systems. That may be dissimilar systems. There are a number of different strategies for meeting the 10 to the minus 9 target, and all very well known. So what are the key questions of system safety assessment? What is the system? System definition. What does it do? What can go wrong? Looking in depth at the potential failure conditions. What happens if it does go wrong? What can cause it to go wrong? Looking at the environment in which it's operating. What is the risk? That's the classification. And can we accept that risk? Does it fit within the boundaries we have set in that proportional relationship? So here is a very basic functional hazard assessment, looking at, say, pitch control of an auto-flight system. You can have the loss of, but we mustn't forget the other failure conditions, like some kind of hazardously misleading information, or when we're dealing with control systems, oscillations or divergent effects, and the effects they may have consequently upon the aircraft in flight. And that's how you identify the various failure conditions. So 3 steps in the standard system safety assessment. First, functional hazard assessment. And second, you get into the number crunching, the safety analysis. But it's not just a question of number crunching. There are, again, a number of different techniques that can be applied, and these techniques are developing with digital twins, with simulation. There is so much more computational technology that we can apply to the analysis process now. And the outputs are a demonstration to the authorities that the system is certificable, but they are also systems limitations. That may be emergency procedures in the flight manual, maybe abnormal procedures, and candidate maintenance requirements, because certain elements of the systems may require regular maintenance, or at least some kind of monitoring. Many different techniques for analysis. We're most familiar, I think, with fault trees, the tool that are most commonly used. Dependency diagrams, design appraisals, engineering judgment still comes into the process as a whole. When you're looking at probabilistic numbers, you may have FMEAs for particular components. You may have a component history. You may not. You may actually be gathering that data and making judgments on the validity of that data, which is where the design appraisal comes in. So putting all of these various techniques together, you can build a believable system safety analysis. And often that's done as an iterative process. It's not a one-shot process, because you may discover something in the analysis which requires you to go back and revisit the design. You may discover something in flight test, for example, that requires you to go back and revisit the design. And so the safety assessment that you provide at the end that results in those outputs, compliance demonstration and limitations and maintenance requirements, may be part of an iterative process. Safety advancement. How do we make the world safer? I was very pleased to see the Thales presentation I remember many years ago, I was with Western Helicopters, Leonardo, working on what was then the H101 that became the Merlin, and the flight control system there, and the displays in the cockpit. But that's seeing some of that large helicopter, large aircraft technology migrating to the smaller vehicles is incredibly important. Back in 2014, we had a helicopter safety team here in Cologne at EASA, and one of the reports it produced was to look at new technology opportunities to provide safety improvements for helicopters in operation. Glad to see in the European Safety Plan, or the Plan for Aviation Safety currently, there's a rulemaking activity which addresses the harmonization of 1309. It's out for comment at the moment. I believe the comments go to you, don't they, Clement? Yeah. So it's for you folks to comment. It has very much the concept of proportionality within it. It brings the same language to ensure consistency across 1309 from the different certification specifications, from the different FARs, so European, US harmonization. It's very much to be encouraged. It recognizes some of the foundation documents that we have as guidance, looking at development assurance. It gives a formal recognition to those documents in the change to the requirements. But, and here is my last point, at the moment, we set safety objectives, we demonstrate that we meet those safety objectives, and then we close the books until something bad happens. And if we have an accident or an incident, we may go back and revisit those safety assessments and say, did we get it right? Did we get it wrong? What happened? Why did this happen? Hey, we had this as this probability, but in fact it seems to be a different probability and outcome. So shouldn't we have a continuous process? If we actually believe in performance-based regulation, then it does mean having a feedback mechanism, at least for the more critical failure conditions, and regularly revisiting the assumptions embedded in the safety analysis. So this would be my call, and the words in quotes there come from a certification process study that was done 20 years ago. And it recommends, really, that there should be a regular review of the assumptions embedded in the safety analysis. And it's not, in the past, that may have been impractical. But today, with the amount of data we have available, with cloud-connected avionics, it's not difficult to do. That's my argument. So thank you very much for listening to me. To sum up, it's not just about the numbers. It's about having a systematic methodology and applying that systematic methodology. System safety assessment has proven itself over the years as a successful technique. It's not just on your to-do list for the certification authorities. Here is a wad of documentation. Yeah, the show me part is part of certification, but it's also to produce a better design. It is about a qualitative method informed by quantitative methods, because there's still that element of sound engineering judgment required. And, as I've mentioned, more data becomes available. So methods and techniques, simulation, digital twins, new ways of approaching safety assessment become possible with cloud-connected avionics. Vast amounts of data will be available to us in the future. That's my message for today. I hope you found it useful, and I thank you very much for listening to me.